Okay, so hi everybody. So today we're going to go ahead and work through 5 and 6 on the data tables for the FRQ reviews for the BC exam. Okay, so here we go. As a pot of tea cools, the temperature of the tea is modeled by a differentiable function h for t between 0 and 10, where time t is measured in minutes and temperature ht is measured in degrees Celsius. Values of ht are selected values of time t are shown in the table above. So as soon as you get a table like this, you should be thinking to yourself a Riemann sum, or possibly like the average value, where they ask you to find like the rate of change of h at say, 4.5 or something like that, or 6.5 or something. You just go between. So you should recognize what type of a question this is going to be in. Okay, so use the data in the table to approximate the rate at which the temperature of the tea is changing. So rate of the temperature, well, that's h prime of t at time 3.5. So I'm trying to figure out what h prime of 3.5 is equal to. So I don't know exactly what it's equal to, but I can estimate it by going around it, right? So 3.5 is going to fall right in there. So all I'm going to do is find the slope of the line between those two points. So if 52 minus 60 all over 5 minus 2. So this is going to be, sorry, I thought I was doing this wrong. So 8 all over 3, right? 52 minus 60 is negative 8. 5 minus 2 gives you 3. So that is what the answer is going to be. Now, what exactly does this mean? Which the temperature of the tea is changing. So this is going to be degrees per minute. Okay, and there we are. Okay, B, using correct units, explain the meaning of 1/10 of the integral from 0 to 10 of h of t dt in the context of this problem. Use a trapezoidal sum with 4 subintervals indicated in the table to estimate what that is actually equal to. Okay, so let's try and zoom out a little bit so we can get the whole table in there and everything. Okay, so what I want to do is I want to use 4 subintervals of trapezoidal sums. Okay, now this is not exactly what this graph looks like, but we'll pretend for a second we know this graph is decreasing. So the graph is going to be coming down like this. And what I want to do is I want to create trapezoids to estimate what the area is underneath this curve. So we're going to go ahead and pick a value there and pick a value there. And then we're going to draw in that straight line there. And so that trapezoid is actually going to estimate what the area under that curve is pretty well. Okay, now what is the form of the area of a trapezoid? So it's very similar to a triangle, which is 1/2 base times height, but a trapezoid has 2 bases. So it's 1/2 b1 parentheses b1 plus b2 times h. So in the context of this problem, this is going to be b1, this is going to be b2, and that distance from there to there is going to be the height. Okay, so what are the bases? The bases are just what these temperature values are going to be. Okay, so, and I have my calculator to use here, so I'm going to go ahead and use it in a second. So I have 1/10 the integral from 0 to 10 of h of t dt is going to be approximately equal to 1/10 times, okay, so I have 1/2 base 1 plus base 2. So base 1 plus base 2, so 66 plus 60 times the height. Now, what is the length between 0 and 2? What's the distance between 0 and 2? That's just simply 2. Plus 1/2, 60 plus 52, times the height, which is 3, plus 1/2, 52 plus 44, times the height there would be 4, and then plus 44 plus 43, 1/2, 44 plus 43, and times the height between those two, which is going to be 1. Okay, so this is equal to. Now, let's try and cancel some things out here to make our computations on our calculator a bit easier. You notice the 2's cancel there. 60 plus 52 is 112. 112 divided by 2 is 56. Hopefully you guys can see that. This 2 is going to cancel that 2 at 2. And that's about it. Okay. So go ahead and go to my calculator. Let's bring it out here real quick. So I am going to have 1 divided by 10. So 1 divided by 10. Open parentheses. Actually, let's make this thing a little bit bigger. Hopefully you were writing down that equation just a second ago. I'm going to go ahead and make this a little larger so we can see it a little bit easier. Okay, so I have 1/10, and then I had 66 plus 60, so that's 126. So 126 plus, and the next one is going to be 56 times 3. Okay, so 56 times 3, and then plus, and then 52 plus 44. 52 plus 44 is 96, so it's 96 times 2. 96 times 2. And then plus, 44 plus 43 is 87, but you have to divide that by 2. So I have 87 divided by 2. And then we close the parentheses and then enter. So you get 52.96. Okay, actually, let me make this smaller. Okay, so this is equal to 52.96. Okay, now let's go back and let's actually make sure we're answering the question. Using correct units. So we don't have any units yet. Okay, so what do? We added up what h of t was. So it's the total amount of degrees, and then we divided by the interval of it. Okay, the length of it. So what we're basically doing is we're finding average temperature. So all this is this is degrees. Okay, what this means, so 52.96 degrees is the average temperature of the T over the time interval from 0 less than or equal to T less than or equal to 10. Okay? Okay, onward. C. Okay, so we're going to evaluate the integral from 1 to 10, or sorry, 1/10 of the integral from 0 to 10 of h. And this should be a prime. I thought I actually switched this, but it doesn't appear so. Okay, so this is h prime of t. And so what are we doing here? So you're evaluating what this is going to be. Now, you don't have a formula for h prime of t, but you do have the first fundamental theorem of calculus. So by the first fundamental theorem of calculus, you know that this is equal to 1/10 times h of 10 minus h of 0. And I just have to figure out what those are equal to. So h of 10 is 43, h of 0 is 66. So this is going to be 1/10, 43 minus 66. And this is 1/10 times negative 23. So this is negative 2.3. Okay, now what is this? Okay, what did I do? I added up the average rate of change, added up the rate of which the temperature is changing, and I divided by the interval length. So what that gives me is it gives me an average rate of change. So 2.3 is going to be a rate of change. So it's going to be degrees per minute. And what this means is over the time interval, over the time interval, 0 is less than or equal to t less than or equal to 10. The t is cooling at an average rate of negative 2.3 degrees per minute. That means every minute it goes along, it should go down on an average by 2.3 degrees. Okay, D. And once again, I thought I corrected this, but evidently I didn't. So at time is equal to t, at time t is equal to 0, biscuits with the temperature of 100 degrees are removed from an oven. The temperature of the biscuit at time t is modeled by the differential function b, for which it is known that this is wrong. It should be b prime of t is equal to negative 13.48 e to the negative 0.173 t power. It's supposed to be raised to that power. For some reason, it didn't get put there. Okay. Using the given models at time is equal to 10, how much cooler are the biscuits than the t? So what do I know? I know h of t, h of 10, apologize, because that's one of the things I want to know. That's the temperature of the t at time is equal to 10 is equal to 43 degrees. So this is 43 degrees. What I want to know is I want to know what b of 10 is. Okay. And I want to compare b of 10 to h of 10. Now, what else do I know? I know b of 0 is equal to 100. So you're given a point. You're asked to find a point. What do you use? The first fundamental theorem of calculus. Okay, so what I'm going to do is I'm going to integrate from 0 to 10 of b prime of t dt. And by the first fundamental theorem of calculus, this is equal to b of 10 minus b of 0. Now, all this stuff I have enough to evaluate. I know what this is. I'm trying to find that. And then this I can just use my graphing calculator for. So I'll go ahead and do that. So I'm going to go math 9, and I'm going to integrate from 0 to 10. Sorry, it's so tiny there. And then I just have to enter in this function. So the function is negative 13.84. And then I have e raised to this power of negative 0.173 t, or x, dx or dt. And so when you do that, you get an answer of, so this is negative 65.8172 is equal to b of 10, which I'm looking for, minus 100. So add the 100 to the other side. So we're going to go as plus 100 here. And so the answer, b of 10, is equal to 34.183 degrees. Okay, so 34.183 degrees. So using the given models at time t, how much cooler are the biscuits than the t? So you have to subtract these two. H of 10 minus b of 10 is equal to 43 minus 34.183 is equal to, so minus 43. I know I'm not going the same order here. That's okay. It's just the difference between the two. And I know my answer is going to be positive. Okay. So the answer is 8.817 degrees. Okay. That's the temperature change between the two, the temperature difference between the two. Okay. On to number 6. Okay. So number 6, a volume of a spherical hot air balloon expands as the air inside the balloon is heated. Okay, the radius of the balloon in feet is modeled by twice differentiable function r of time t, where t is measured in minutes. For t between 0 and 12, the graph is concave down. The table above gives selected values of the rate of change of r prime of t, of the radius of the balloon over the time interval from 0 to 12. Okay, the radius of the balloon is 30 feet when t is equal to 5. Well, that's a coordinate, right? So I know r of 5 is equal to 30. They're giving me a point. I bet you in a little bit they're going to ask me to find a point. Okay, and we know how to do that. Okay, the volume of the sphere of a radius is given by that equation. So estimate the radius of the balloon when t is equal to 5.4. Okay, so what are they doing? They're trying to ask us to find r of 5.4. Okay, using a tangent line approximation at t is equal to 5. Okay, so it's a little bit different. Before, what we do is they're giving me a point, they're asking me to find a point. We'd use the first fundamental theorem of calculus, but they actually don't give us quite enough information here. And so they're asking us to do it a little bit differently. Okay, so I need to use a tangent line approximation at t is equal to 5. So what are the two things you need to know in order to come up with the equation of a tangent line? You need to know a point. So I need to know what r of 5 is, which I know is 30. And I also need to know what r prime of 5 is, because that's the slope. Well, r prime of 5, if you go up here, is equal to 2. So you have an equation, and it's going to be, so what are my two variables here? R and t. So I have r minus the r value, so 30 is equal to the slope, 2 times t minus 5. Okay, so that's the tangent line at t is equal to 5. Now all I have to do is I just have to go ahead and plug in what 5.4 would be. Okay, so r is equal to 2 times 5.4 minus 5, and then I added the 30 to the other side already. So r is equal to 2 times 0.4 plus 30. So r is equal to, so this is 0.8. So I have 30.8. Okay, so estimate the radius. The radius is approximately 30.8. And this is going to be feet. Okay. Now, it does state, is your estimate greater than or less than or equal to the true value? So what do we have to pay attention here? It says the graph from 0 to 12 is concave down. That means the graph will be either something like this, or perhaps it would be going up, but it's going to be like that. Okay. Now, in either case, when I do a tangent line to that curve, the tangent line is going to be up above, which makes it an overestimate. Okay. So is your estimate greater than or less than the actual value? Give a reason for your answer. Okay. So this estimate is an overestimate. This is because r of t is concave down. Okay, B. Find the rate of change of the volume of the balloon with respect to time, with time is equal to 5. So I'm trying to find dv dt when t is equal to 5. Okay, indicate the units of measure. So what do I need to do this? I need an equation for volume. Well, lucky for me, I already have an equation for volume. Is given right here. V is equal to 4/3 pi r cubed. So V is equal to 4/3 pi r cubed. So then taking the derivative here, I have dv dt, taking the derivative of this thing with respect to t. So I bring down the 3. So I have 4 pi r squared, but I took the derivative of r with respect to t, so I need to have dr dt in there. Okay, so then I'm going to evaluate dv dt when t is equal to 5. Well, this is equal to 4 times pi times the radius at 5. Oh, I know what the radius of 5 is. It's 30 right here. It's one of the pieces that was given. So times 30 squared, and then times dr dt, and dr dt has to be evaluated at 5 as well. Well, I know what dr dt evaluated at 5 is. It is 2. So this is just going to be times 2, and then I just have to evaluate this out. So this is equal to, we have 8. 4 times 2 is 8. 30 squared. 3 squared is 9, and you have 2 zeros on top of that, so it's 900. So it's 900, and then times 8 there. So 8 times 900 is 7,200 pi. And then find the rate of change of the volume. So it's volume, so it's going to be cubic feet per minute. Okay, so that's what the rate of change is going to be. Okay, C. Use a right Riemann sum with 5 subintervals indicated by the data in the table to approximate what this would be. Okay, using correct units, explain the meaning of this in terms of the problem. Okay, so write Riemann sum this time. Okay, so the integral from 0 to 12 of r prime of t dt is going to be approximately equal to, okay, so it's a right Riemann sum with 5 subintervals. So we have 1, 2, 3, 4, and 5. So the lengths are going to go 2, 3, 2, 4, 1. 2, 3, 2, 4, 1. So we have 2, 3, 2, 4, 1. If you don't like what I'm doing, don't do it this way. I just don't want to flip it back and forth so many times. Okay, so right Riemann sum. Okay, so the first interval is 2 times the right, so times 4. Okay, and then plus, so the next interval is 3 times the right, which is going to be 2, plus 2, so the length from there's 2 times the right one, which is 1.2, plus 4, that's the length from there, times 0.6, plus the last one, which is 1 times the right, which is 0.5. Okay, so this is equal to, so 2 times 4 is 8, plus it was 3 times 2, which gives you 6, plus 2 times 1.4 is 2.4, plus 4 times 0.6 is going to be 2.4 as well, and then plus 0.5. So this is equal to 14, 16.4 plus 2.9. So this is going to be 18, 19.3. Okay. Now, using correct units, explain the meaning of what this is. Okay. So what are we doing? We're integrating the rates over the time from 0 to 12. Well, that's going to tell you the total change in the radius. So this is 19.3 what? Feet, because that's what the radius is measured in. Okay, so on the time interval, from t is equal to 0 to t is equal to 12, the radius changed by 19.3 feet. Okay, so it got bigger. Okay, by 19.3 feet. Okay, D, is your approximation of part C greater than or less than that the actual value? Give a reason for your answer. Okay. So what we did is we're estimating what r prime of t was. Okay, let's go back and let's look at the values. So r prime of t is progressively getting smaller. Okay, so it's going down. So the graph as we go from left to right will be going down. And so we have two different options, right? It could go like that, or it could go the other way. Let's take a look at both cases. Okay, or it could be going, kind of going like that. And what I want to do is I'm come up with a right Riemann sum. Okay, so let's use a right Riemann sum. So if I draw a rectangle like this, remember it's going to be determined by the value on the right. So it's actually underneath the curve, underneath the curve, underneath the curve. So it looks like this is going to be an underestimate. Let's go ahead and look down here. Okay, so if we did a right Riemann sum here, it would also be an underestimate. Okay, so our estimate of 19.3 feet is an underestimate of the integral from 0 to 12 of r prime of t dt for two reasons, or two combined reasons, because r prime of t is a decreasing function, and we are using a right Riemann sum. Okay, so there we go. That is the last two that we'll go over with data graphs. Hopefully you guys are good with those, and we'll see you next time. Bye, everybody.